here. So it looks like when you go to homework, you can't act, well, this PA, sorry. When you go to homework 1, if I can go, you can, it looks like when you click on homework, you can't open it. So the quick fix was just now, I added the PDF file right under. So this. But you have to go through inside the homework and read what's going on. So quick explanation. Some of those you might say, oh, I don't know what to do, because usually when I give homework, part of it you already can do it, and then some you can, but it's what's happening in the future. So you know what you have to listen to or understand. Like this topic, I have to absolutely understand because there's homework about it. So you should be able to do those two. You should be able to do this one. We already did it. And then this is something that I'll talk today if things work. If not, it's Monday. It's due next Monday, so we will get there. Don't worry. Usually homeworks are due on Wednesday, but because we had it one day like off, so I made this one to be due Monday, September 19th. So you have plenty of time. All right. So don't be concerned if you see that some of these are you can't do them. And minimize, yes, I know that. All right, that's it. Let's quickly go to this, and whenever things turn off, they turn off. So your class participation, I'll talk about it first. So we know that you can do that one over the weekend. You still need the passcode. If you're in the classroom, I give you the passcode. So if you're on Zoom, I'll figure it out. All right, you all remember the rotation matrix from Wednesday, right? We talked about there are 3 ways of using them, common methods of using them. Basically, this is a quick review and catch up of what happened on Wednesday. All right, so rotation matrices, they can represent coordinate transformation, right? So if you have point P with respect to one frame, you can move it to another frame. We talked about that. It can give the orientation of a transport frame with respect to a fixed frame, right? So if you have a frame, you say rotate 45 degrees about Z axis of this fixed frame, you can do that using the rotation matrix. It also acts like an operator. Do you remember the vector that we use in my dog that flew into the windshield? So it acts like an operator. You can rotate a vector from one frame to another. Basically, you can see if you change your reference frame, what would be the direction of that vector into another one, or if you rotated everything, how it would look like. So it works both ways. Now, the other concept that is interesting and very useful in use of rotation matrix is called similarity transformation. So it basically means that if you have a linear transformation in one frame, and you want to know what's that transformation in another frame, you can use similarity matrix, because the transformation is the same, is similar. Just the point of view is changing, but we can write a mathematical equation for it. So if we have the reference frame rotation and one of the matrices, we have the other one. All right. It's good if you have a camera again, the robot, the arm, the reference frame in the corner, and you want to know, okay, this car turned left 45 degrees. That's what the fixed frame sees. I want to know what the camera sees. So you can use this relationship. So if A is the matrix representation of your linear transformation in your frame 0, the original frame that this happens. So this guy, you would sandwich basically that transformation, that linear transformation between the rotation matrix from 0 to 1, so old frame to the new frame, and the inverse of it, which you know is the transformer, right? So basically, if you can post multiply and pre-multiply the same thing, then the resulting matrix is going to be your similarity matrix. It's going to be the matrix in your frame A and the transformation, right? So now, if you have B, you have R 0 and 1. You already have this one. You can find what A is. So this means if A is a rotation matrix, so this applies to all transformations. As long as there's a new transformation. Now, if A is a rotation, B is also going to be a rotation, just from a different perspective. That's basically what it's saying. All right. Now, your cost participation, which is like a longer, usually Fridays or due next class, it's about this. But this slide is enough to do that one. There's a little bit of like calculation involved, but all you need is what you see on the board. All right, I'll give you the password once this turns off. Then you can go also home. All right, quick example of what all these mean. If we draw our original axis, and then if we rotate this frame to some other frame, let's say my new frame is going to be Y1, then Z1, and then X1, right? And I have a point P that I know, or so this could be a point P or a vector that is calculated from the origin to point P, right? You can see it either way. Since it's from the origin, it doesn't matter. So if this rotated theta in your in one of your frames, you want to know how much it rotates in the other frame, or what is the transformation in another frame. Our original frame is frame 0. We showed such, so x0, y0, z0, and then our new frame is frame 1, x1, y1, z1. Then R01, you should be able to calculate this, right? Because you can see, finding from projection method, any of those methods, you can find R01, -1, 0, 0, 0, 0, 1, 0, 1, 0. So this is rotation of point P. So that's your rotation matrix. Now to find the rotation of P, we know that rotation of around z-axis for theta degree, right? So if P was, if you're rotating it about z-axis for theta, is going to be similar to rotation in y-axis and theta. So this is your, so if you remember, we said B and A. So if this is B, so if your original was A was the rotation that you had, you sandwich it between 0, 1 inverse and 0, and it gives you B. So it gives you the rotation in the new frame. So anytime you have two frames and you want to see rotation in one, means what kind of rotation in the other one, you can use this. The only thing is that you need to find the rotation between. You can move, transform anything in that frame to the new frame. A vector, a point, a rigid body, if you have to even do the path of a car, for example, in one frame to a new frame, you can still use this. Because you could assume you're using discretization, so it's point at a time. So the location or coordinate at each time step. You move those time steps, those points becomes your new path. All right. So a lot of time in robotic, we actually don't solve things in continuous time domain. We discretize it. We define the time step, and then we solve for that time step and go to the next one. Now, the smaller you can get, the more accurate it is. The smaller time domain means more calculation, so higher purchasing power. That's why there are different types for robots, depend on their CPU, right? But you can use the calculation power. Now, the fun part begins from here when you become familiar with Euler angle. So we can parameterize our rotation in, well, two distinct ways. One is when we use 3-parameter rotation. The other is when we use 4-parameter rotation. 4 is called quaternion. And 3, that there's only one way of doing quaternion. Then 3-parameterization, we can follow many combinations or methods. We are going to talk about 3 of them only today, and we will stick to them. And you might see different ones in the literature, and they're all kind of the same concept. So it should help you if you study these. It should help you to read like literature for other ones. So when we have 3 independent quantities, we can define our rotation as Euler angle. We can use roll pitch yaw. We can use axis angle type of rotation. What does it mean? It means that I'm here. Close your eyes, all of you. Don't cheat. Close your eyes. Everyone. Now open your eyes. How did I rotate? Can you tell me, like, how did I rotate? You can't. You just see where I am, right? So you remember where I was. You see where I am. So you have 2 rotation matrix. You can define from one of these ways what are the possible rotation that takes me there. You don't need to know exactly what I did, because I could have done this and this, and I did here. For you, you can do it with 3 rotation using Euler angle or roll pitch yaw. Well, I did not roll or I just yaw, but it could be like 1-1 and then just a yaw. And axis angle, which is the most useful and the most complicated. All right. Or we could use quaternion, which are 4 independent quantities, and you write them in the form of A plus BI plus CJ plus DK, which those are real numbers, and then IJK are your basic quaternion, and they have this relationship. Okay. I will see how the class goes. I will talk about those 3 first, and if like everyone was like, yes, they're easy, but let's do more, then I will do more. All right, because this might be the first time you're exposed to something like this. You might not sense it physically. I like things that I can sense physically and understand. All right, so we go with those 3, and then we'll see the value and be back again. All right. Now for Euler angle. So here's the thing. You remember I said I'm here, then I'm here. You don't know my rotation. You just need to find a set of rotations that get you from rotation A to rotation B. The orientation A to orientation B. Now, Euler angle, if you, okay, let's set up camp. Our fixed frame is frame S, right? So we want to frame 0. We want to identify those first, and frame 1 is my rotated frame. So when you're looking at those, so 0 was your original, and 1 or A, B, C, those are your rotated ones. So frame A, B, C, those are the rotated one. I'm calling them frame 1 because after you're done with rotation, you'll end up in 1. Now, if you followed, so Euler angle rule says that use 3, well, you have to write letters for the numbers less than 10, right? Use 3 consecutive rotation in the current frame. So current frame means that you will post multiply all those rotations such that you're going from 0 to 1, which is your rotated frame, through rotation A, rotation B, and the last one, which is itself. So I'm not going to put A, B because I didn't put C on the last one. So it's A, B, and 1. So forget about A, B, C. So going from this orientation, Z0, X0, and Y0 to this orientation, Z1, Y1, and X1. So to go here, you can have the first rotation about Z-axis for phi angle, then consecutive rotation, current frame, so post multiply by rotation about Y-axis for theta, post multiply by rotation about Z-axis for psi. Now this is called RZYZ, right? This is Euler angle transformation. Now this is one of them. There are 6 of these possibilities that you can check to see if you start from frame A, which of these 6 you will end up in B. There will be one that takes you there. You just need to figure out which one it is. So the other ones are YXY, XYX, ZXZ, YZY, and XZX. And that one, that's the last one. So 6 of them. So what do you see in common in all of these? What's the pattern that you see? So the first and third rotation are about the same current axis, right? So you can change the one in the middle. So if depending on the final orientation, you can kind of guess which one of these will end up, right? And you can use multiple Euler angle rotation as well to go from one point to another. Do we know what this is going to be? Do we have the matrix for this one? We have, because these are all principal rotations, right? Sine, cosines. So you actually know what R01 is. So you know what R01 is. You know where you started. You basically have to find the root. Right? So you always go back to the basics. You see that doesn't matter how much we propagate and add things, you always have to solve it backward. So simplify, 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 and which is matrix multiplication. All right. So that's one method. Method number 2, it is roll, pitch, yaw, or take Bryan angles. Now, how many of you have used roll, pitch, yaw, or the concept? Especially if you're ME or MAE, you have used, right? So airplanes are a very good example because that's what they use, roll, pitch, yaw. Sorry. It's kind of similar concept, but here we are gonna call RZ and phi as our yaw, Rx and psi as a roll. So when I say Rx and psi, what do I mean by that? What do I mean by Rx and psi? For angle, psi angle, right? So notations are really important. And Ry and theta is going to be your pitch. Now, roll, pitch, yaw happens also in the current frame. So current frame rotation, meaning that you post multiply, right? We are going to have Rx, Y, Z. So we're going to have 2 different ones. Okay, we could have roll, pitch, yaw. We could also have yaw, pitch, roll. Now, roll, pitch, yaw is going to be in the current frame. Yaw, pitch, roll is going to be in our fixed frame. Now, again, you can't write a combination. You just need to remember if you are doing fixed frame, you pre-multiply. If you're doing current frame, you post-multiply them, right? So your roll is about x-axis, right? So Rx psi, then your pitch is about y-axis, Ry theta, and your yaw is Rz theta. So that's one combination in current frame, so they post multiply. Now, yaw pitch roll in fixed frame will be the same one, right? Just backward. So it will give you the same rotation matrix again. Here you can, so why do we use